This is a presentation about the mole. You might have seen this picture of the mole in our chemistry classroom, or one similar to that, or on the chemistry mole bucks. And you probably recognize the mole as a furry little creature, but in chemistry it has much more significance than that. So what exactly is the mole? Well, the mole is considered a bridge. And if you think about a bridge connects two things. So the mole is a concept that connects two different ideas in chemistry. On one side, we have the microscopic world, or really the submicroscopic world. That would be atoms, molecules, ions, things that we can't really easily deal with in lab. If I were to ask you to go to our high school chemistry lab and count out 10 atoms of carbon, you would have an impossible time doing that. On the other hand, if I asked you to go to lab and measure out 10 grams of carbon, that would be pretty easy. So the bridge is the mole, and it's connecting the submicroscopic world with the macroscopic world. Looking at this in a more visual way, we have grams on one side, particles on the other side, and the mole in the middle, the connecting piece, the bridge. To go from grams to particles, you have to go through the mole. So what exactly is a mole? Well, the mole is a counting number. You're probably familiar with counting numbers. If you go to the grocery store, you get a dozen eggs. That's 12 eggs. You go buy a pair of shoes. That's 2 shoes. A ream of paper, 500 sheets of paper. These are convenience terms. They all have numbers that go with them. In chemistry, the mole is actually a really huge number, 6.022 times 10 to the 23rd. So if we had a mole of water molecules, that would equal 6.022 times 10 to the 23rd water molecules. If we had a mole of carbon atoms, that would be 6.022 times 10 to the 23rd carbon atoms. And take a moment here just to talk about the abbreviation for mole. Up here I have mole with an E. Chemists abbreviate mole by dropping the E. It's kind of silly, but that's the way it's done. So it turns out that this number, 6.022 times 10 to the 23rd, is really important. In fact, it's so significant that it has a name. You might have come across another number with a name in your math classes. 3.14 you'll recognize as pi. So what is the name for 6.022 times 10 to the 23rd? It's called Avogadro's number, named after Amadeo Avogadro. The abbreviation is capital N with a subscript capital A. And once again, just to get it in your head, it's 6.022 times 10 to the 23rd. This is actually a really huge number. If you took the time to write it out and to move the decimal place 23 places to the right, because that's what 10 to the 23rd means, and you added in all those zeros, it would be really long, and it would be really impossible to count that high in any kind of reasonable time frame. In fact, it's so huge that it's really only reasonable to talk about the mole when counting really small things, atoms, molecules, and ions. It would be inappropriate to count a mole of pencils. Let's look at why. So how huge is it? Well, 1 mole of hockey pucks would equal the mass of the moon. If you had a mole of basketballs, 6.022 times 10 to the 23rd basketballs, you'd need a bag the size of the earth to hold them all. And even if you had a little small penny stacked up, they stack up really well, it would cover the entire surface of the earth 1/4 mile deep. So the mole is an inappropriate counting unit for our macroscopic world. It's only for that microscopic that we use the mole. Oh, a quick shout out to Christy Johannesson, a fellow chemistry teacher who created this slide that we're looking at, which is good with animations. All right, on to the next thing. So we talked about one side, the mole and particles. 1 mole is 6.022 times 10 to the 23rd particles. Let's talk about the other side of the bridge. How is the mole related to molar mass, or related to the mass? It's related by molar mass. Look at this word, the root is mole. Molar mass is the mass in grams of 1 mole of a substance. Where do we find that mass? Our handy-dandy periodic table. For elements, we can find the molar mass on the periodic table. Take out your periodic table right now and find carbon. In its box, you'll see the capital C, the chemical symbol. You'll see the whole number 6. Remember, that's the atomic number. that equals the number of protons, and you'll see a number with decimals. Yours probably says 12.011. That's the atomic mass, the average mass of carbon, and it's related to the molar mass. 1 mole of carbon atoms equals 12.01 grams. Carbon has a molar mass of 12.01 grams per mole. That's just another way to say that. Depending on what periodic table you look at, there might be a bunch of decimal places in the mass. Our textbook uses only 2. That sort of simplifies things, so I'm going to follow that convention of just using 2 decimal places to the hundredths place to keep things easy. Okay, back to the periodic table. Find lithium and find its molar mass. So 1 mole of lithium atoms equals 6.94 grams. In other words, lithium has a molar mass of 6.94 grams per mole. Let's put this all together, both sides of the bridge, in what we call the mole roadmap. We have our mass related to particles by way of the mole. The mole is the connecting piece. So let's summarize what we've talked about. Relating moles to mass, we use the molar mass. Our equivalence statement for this is 1 mole equals some number of grams, some number represented by x. Where do we find those grams? We have to look at the periodic table. So for carbon we get one number, for lithium another number. Every element is going to have a different value. On the other side of our bridge here, we have Avogadro's number that relates moles to number of particles. Our equivalence statement down here, 1 mole equals 6.022 times 10 to the 23rd particles. No matter what element or compound you're talking about, always 1 mole is Avogadro's number worth of particles. Okay, let's put this together in an example. So our first example is, let's say that we have 6.5 grams of carbon. We want to know how many atoms of carbon that is. Well, let's look at our mole roadmap, and let's start with our given and figure out what we need to do. So we always write down our given to start with, 6.5 grams of carbon. Grams, we find it on the mole roadmap. Grams right here. We're going all the way over to particles, atoms in this case. So this will be a 2-step problem. Grams to moles, moles to particles. So to start off here, to go grams to moles, we have to use the fact that 1 mole for carbon is 12.01 grams. Remember, I got that from the periodic table. We need to remember how to plug this in to make it work. Remember, with conversions, we have to make our units cancel. So we want to have grams, since we have grams on top, we want to have grams on bottom. If we put our 1 mole on bottom, it wouldn't work out. So we'll put our 1 mole on top and 12.01 grams on bottom. Grams on top, grams on bottom, cancel out. Okay, on to our next step. To go from moles to particles, we're going to use 1 mole is 6.022 times 10 to the 23rd particles. Well, our unit here that isn't crossed out is the mole, so down here we have to have the mole to cancel out. So 1 mole is going to be 6.022 times 10 to the 23rd. Now I'm going to go ahead and write atoms, because that's the kind of particle that we're talking about. Alright, let's switch from our pen to an arrow and open up our handy-dandy calculator. Whoops, pretty big there. Okay, so let's type in what we've got. We've got 6.5. Remember that everything on top is going to be a times, everything on bottom is divided. So times 1 divided by 12.01 on to the next part, times 6.022 times 10 to the 23rd. I always use the EE key because it's more efficient and it takes care of some problems that we sometimes have when you have this number in the denominator. So let's go ahead and hit enter and see what we have. 3.25 and a bunch of other numbers, e plus 23. Remember, this means times 10 to the 23rd. We can't leave that off, because if we did, we'd be saying 6.5 grams of carbon was equal to about 3 atoms of carbon. Think about that. That would be about 2 grams per carbon atom, and that's totally unreasonable. So we've got to remember this end piece. We're going to have to do some rounding. We won't write all this down. We have 2 sig figs right here, so we need 2 sig figs in our answer, so it's going to be 3.3 times 10 to the 23rd. So let's write that down. 3.3 times 10 to the 23rd atoms. Reality check, is this reasonable? Well, 1 mole of carbon is 12 grams. We're starting with less than 12 grams. So if 1 mole is 6.022 times 10 to the 23rd atoms, we should end up with less than that number of atoms. And indeed, we do. So we're good. Let's go on to another example. This time, atoms to grams. If we put in our mole roadmap and we write down our given information, we've got 5.1 times 10 to the 22nd atoms of magnesium. This time we're not starting at grams, we're starting at particles, at atoms. We're trying to get to grams, so it's going to be 2 steps again. Atoms to moles, moles to grams. Our first step, atoms to moles, we use this equivalence statement. Well, how do we fill it in? Atoms on top, we have to have atoms on bottom, so we're going to write 6.022 times 10 to the 23rd atoms. On top, we're going to write 1 mole. Our atoms cancel out. Our next step, we already went particles to moles, now we go moles to grams. 1 mole is some number of grams. Well, we've got to look at our periodic table for magnesium. Magnesium is 24.31 grams. So we've got to put our 1 mole on bottom, because 1 mole on top and on bottom cancels out, and 24.31 grams. All right, calculator time. All right, so here we go. 5.1 EE 22. On my graphing calculator, I have to hit a second function to get that EE button. Okay, times 1, everything on top is times, divided by 6.022 EE23. Let's stop here for a moment. If you don't like this EE key and you use times 10 raised to the 23rd, you must use parentheses. If you don't use parentheses, the calculator gets confused and thinks the times 10 to the 23rd is on the top, not divided by, so you'll get the answer wrong if you don't use parentheses. Okay, then it was times 24.31 divided by 1. And our answer is 2 point something. We have 2 sig figs over here, so our answer needs 2 sig figs. It's going to be 2.1. So let's write that in. 2.1 grams. Is that reasonable? We start with less than a mole, less than 6.022 times 10 to the 23rd. And so we should end up with less than 24 grams. Less than 24 grams, that's reasonable. So, that's our second example. I hope that you learned something about the mole, and now you can get started on your homework.